Okay, here we are for the third big idea, which is the normal distribution. Sometimes we call it a PDF or a probability density function. I don't want to get too technical there, but you just sometimes you'll hear that term. And we use these to calculate ultimately normal probabilities. So this one's going to be a little bit longer. I'm going to try to move quickly. Remember, you can always use pause and scroll. Um, First of all, we want to recall the idea that lots of data that we collect. It's just a law of nature, just an observation. So many data that we collect follow this bell pattern here, symmetric. And so it's so often we call it normal. And so here again, I had just some about I went to a data site and got some uh, data generated. But so let's just say we had like 1,100 people, males that we measured them in terms of inches. And so there are literally 100 or 1,100 dots here in this diagram. And you could see that, we do have some extremely tall people, extremely short people relative to the average, but on average, they're about 65 inches tall. And on average, we deviate about 2.44 inches from the mean. Okay, so we see this pattern often when we're taking a look at data. Now, if we consider a random variable such as heights or times or weights, we call this continuous. And the reason is that theoretically, if we had material to measure the the heights to even a billion decimal places, we could go on and on and on. So theoretically, there are infinitely many heights that we can take on. Now, usually we round that to the nearest half inch and so forth. But, just to get the idea that a continuous random variable is one that can take on an infinite amount of values. And so we typically consider intervals when we're finding probabilities for those. So that's kind of like something you just got to kind of sit right, get right in your mind first before we go on here. Um, so if we would, just say sample from this group, randomly select one of them, okay, we could look at this as, like I said, their heights or, from any population, I should say, maybe let's just pick a bigger one, the United States and randomly select somebody and record their height. We could look at that as a continuous random variable. There's, theoretically infinitely, values it can take on for that individual, but like I said, they are going to follow a pattern. Okay. So we're going to study random variables that follow this normal distribution. So we're going to learn a couple things about it. One is that here's the formula for it, and you're never going to have to use this. But if I wanted to plot these things, as long as I know the mean and standard deviation, mu and sigma, I'm going to get something that's going to plot like a bell-shaped curve. Okay, so there's a unique normal distribution for each population with a distinct mean and standard deviation. So, we call these normal distribution curves. These are the equations. Again, this is what mu and sigma represent. So here's just how they would compare to one another. Here are two with the same mean at 0, but different standard deviations, right? So as the standard deviation gets bigger, on the blue one here, it's a little bit more spread out. The reason it gets a little bit shorter is the fact that, remember, in order to be a probability distribution, the area has to be or add up to be 1. So if we start shifting some of the area out to the side, we got to compensate by getting it lower in the middle, so to speak. Here are two with the same standard deviations or same spread, but that they have different means. Here we have a mean or center at 0, or a mean or center at 2. All right. Again, I'm going to go quick, so pause and scroll as needed. One of the things that all normal densities have is that if we move out one standard deviation, we have about 68% of the data or the area or the observations, whatever term we want to use there, interchangeably lying within one standard deviation of the mean. If we move out two standard deviations, if we add all these numbers up, it's about 95%. Okay, so 95% of those observations or the area are going to lie within two standard deviations. And then just about all of it, 99.7, is going to fall within three standard deviations. So that's a characteristic of all normal distributions. This is an activity that I always did in my other stats classes. And again, this is going to be somewhat abbreviated here. But what I'm going to do is, oh, excuse me. This would be results of, let's say we had 100 students, okay? And we measured their heights. And this was the distribution of them. And we counted them all up. And I can ask questions, and this is where you want to pause, like what proportion of students are 68 inches or taller? And, you know, there were 24 of them. I take 24 divided by 100. I get about 24%. And so, you know, what I could say is that, you know, I can also word this as, well, what is, if I just randomly chose one, what's the probability of getting someone 68 inches or taller? Well, again, since 24% of the students fall within this range, so to speak, then I could say that probability is going to be about 24%. And if we had a different set of data, you know, we would see that this pattern would be pretty much the same. And so those probabilities and proportions would be about the same. And if I calculate those areas and I divide it by the total area here, so if I take 24 and divide it by 100, I get about 24 because each of these bar lengths are, or bar widths are 1. Okay. So that's, you know, again, just some normal data. So what we want to do is get the idea that we can model this with a normal density. All right. But you're saying, well, how is that possible? Because these areas here are like add up to be 100. And we want the area to be 1. Well, that's when we take a look at a relative frequency. So relative to the whole group, 1 out of 100 is 0.01, 2 out of 100 is 0.02. And that's why I picked these numbers, so we don't get bogged down in the arithmetic. But you can see I can go through the same questions here, okay, that I did on the other slide. And only now I have this relative frequency distribution, all right, where we have, again, these you know, bars that are just a little shorter. But notice if I add up all the areas of the bars here, it would add up to 1. Okay, so now I can look at it as a probability distribution. Well, what we're going to do is kind of superimpose this relative frequency distribution with a normal curve. And this is what I did. This is all in the TI-83. So you could see if I plotted the normal density with a mean of 66 and a standard deviation of 2.8, and that's just coming from calculating the, let me see, I think I did that back here. You know what I did, but well, if I took all the data and I calculated the mean and standard deviation, I forgot to include that slide in here. Sorry about that, but you just have to trust me on this one, that the mean is, oh, here it is right here. I just calculated it. Sorry about that. The mean is about 65.56, so we just rounded to 66, and the standard deviation is about 2.815, whatever, so we rounded to 2.8. And notice if I take this and plotted this function, either by typing this in, or in this case, this has built into the calculator. And I don't want you to get too bogged down because you're not going to have to do this, but all I want to do is illustrate that that relative histogram can be modeled very closely with this normal curve. And if I found the normal curve, the area underneath it from 68 and beyond, remember, as long as I go more than 3 standard deviations from 66 here, so I'm pretty far out here, okay, all that area, I'm going to get about 23%, which is really, really, or 23.7%, which is really, really close to these 24s that I got here earlier, okay? So the idea is that we're using this normal curve to model the distribution of these data. And I can answer, you know, questions about proportions or probabilities. The answers are the same. It just depends on how the question is worded. by using this without using all the data. Okay, and we'll see those in some examples coming up here, in the other videos, and I think I even have one here. One more thing here too, if I got into Staplet and I plotted the binomial distribution, it has an option to plot or hide the normal curve. Here I have it plotted. Notice we can even model binomial distributions with a normal curve. And that gets to be very, very useful when n gets large. Now, if n's small, the normal approximation to it is not very good. And there's some criteria for that. It's basically n times p. If it's 10 or more, it's going to be a pretty good approximation. So if I take n times p here, I get, 20. So, it's going to be a pretty good approximation. You can see that that normal curve runs right along with that binomial. Okay, so remember, we're not doing specific problems here. We're just showing you the big idea of where this normal density fits in. Here's just the last thing, or last couple of things here. Yeah, I've got 2 more slides here. Okay, so one is that if I have this normal distribution, all right, and I want to find the area between 7 and 13. I can do this in Staplets very easy, or Staplet very, very easily, okay? All I do is I get into normal distributions. I type in a 10, I type in a 2 for the mean and standard deviation. I plot the distribution, and then I want to calculate area between these values. So here's 7 and 13. And notice it gives me these z's here. I'm going to get into that in a second. But if I calculate the area, I get about 86.64%. So if I were to do a probability problem, I say, what's the probability of getting whatever x represents an x value between 7 and 13, or including those values as well? It's about an 86% chance if I randomly selected that out there, or out of a group of whatever it is that x represents. Okay, we just don't have any context here. We'll see that again in the future examples. Where z turns out is, you have to think that prior to I could say because I started teaching in 1990, way before that time. We didn't have calculators and programs to do this. We didn't even in the 90s. This software didn't really become available here. Staplet's only been out, I don't know, maybe I want to say about 10 years or so, if that. And we go back even the early 2000s, this technology wasn't available. And so what we had to do is convert everything back to the normal distribution, because in the books, and I don't want to get too bogged down into this, but there are tables. If you think about it, Ben Franklin studied statistics. He wasn't able to just punch in something into a computer. He had to look up probabilities on the table. And so what they did was make a bunch of areas for, between values z, or actually it was to the left of z. And we could use these tables to calculate these variables as long as we transform this one back to a normal standard, which would be a mean of 0 and a standard deviation of 1. So in other words, I could do this same thing. The probability of getting something between 7 and 13 is going to be the probability of getting something between negative 1.5 and 1.5. Right? Now, where did that come from? Well, if I just take my observation here, which is 7, I subtract the mean, which is 10. So 7 minus 10 would give me negative 3 divided by 2. That's negative 1.5. And if I put in a 13 here, I take 13 minus 10, that's going to be 3, and I divide by 2. That, again, is going to be 1.5. And so the area between negative 1.5 and 1.5 for this distribution is going to be the same as the area between 7 and 10 on this distribution. Okay, so I really didn't need, okay, again, because I wouldn't have something that was in the table. I didn't have software. I would have to go back and convert these values, 7 and 10, or 13, excuse me, to these z values using this formula, and then go look up the areas on the table to actually get these probabilities. All right. Now I'm just going to use the software. I did use the software here. So mean is 0 and standard deviation 1. I go from negative 1.5 to 1.5, and notice those values are the same. Okay. Now, there's a lot there that I usually take a lot more time to explain, but I'm trying to give you the abbreviated version of why in the world would we be dealing with this Z thing. So uh, it, your examples do address this in your Alex problems. So I just wanted you to have some sort of explanation of where this is coming from and why it's probably not necessary to be able to use it if, again, to go ahead and do all this stuff if you have this software with you, which you will. But your Alex addresses that, and sometimes these statistics courses do go back and address historically, the way things were calculated. All right. So this actually is an Alex problem. I thought this would be the best way to end this. And, so, um, here's a probability, and they call this the advanced one. But so the scenario is we have a civil engineer, and she is measuring temperatures here. And she says that, or we're given that, they follow a normal distribution, and the average temperature of the asphalt is 108 degrees, and a standard deviation is 16. All right. So it says use this to find the percentage or the probability of the noonday temperatures of the asphalt being between 104 and 132 degrees. Okay. So, we might have some sort of parameters, like if it falls within this range, it's okay, it's safe to work on, or something like that, or maybe this is the caution zone. We're not really sure. We're not engineers, but this is the problem presented to you. All right. So it could be done very easily, again, using Statlet. So all I need to do is type the mean and standard deviation in, and I find my left bound at 104 and my right bound at 132. And therefore, I would get 53.19. And that is the Alex solution as I illustrate here. If you got in the explanation, they're going to take you through standardizing this. Okay, so I would have to find the standard value for 104. And so if I subtract the 108 and divide by 16, which are the mean and standard deviation, I would get a negative 2.5. And same thing over here with the 132. I get a 1.5 when I subtract 108 and divide by 16. And so what we're saying here is that if you didn't have that, you would have to find the area between negative 2.25 and 1.5. And you would have to do that arithmetic before you found out what it is that you're looking for. And even if I use, like the if I looked up the 1.5 on the table in the book, okay, I would get this value here that your calculator can do. And this is the Alex calculator. So it finds a probability, but you're restricted to only Z being less than a specific value. And so how we do this is we're going to take the area to the left of 1.2 or 1.5, which is from here over to here. Then we subtract the area to the left of negative 0.25, which is from here to here. So it's like, well, I want this green area. So I'm going to take all this area and take away this little white chunk of area, and that's going to leave behind the blue area. And that's what I'm doing here on the calculator. So this gets a little, that's why they're calling this advanced. Okay, it's not a direct calculation. We've got to do a little bit of thinking here. All right. And if I hit my enter button, which I'm not, which I didn't do because then it erases the entry. I wanted you to see the entry on the calculator, how to do it on the Alex calculator. But this would give me 0.5319, which is the same as 53.19%. Okay. So again, this is a lot that's getting thrown at you very quickly, but it can be confusing. If I mention, I want you to be aware there's an easy way of doing this, all right? But also that there's a more complicated way, and it's a way that your Alex instructs you to do it. So this is very easily, to get confused, okay? And I could have just said, not even showed you this, but this really illustrates the concept very well. And that is, this is the probability or the percentage of noonday temperatures that, whatever way you want to phrase that question, that fall between 104 and 132. And it's It's real easy to calculate that. And we'll give you some more examples like these in subsequent videos. Okay. I know this is getting a little long. I wanted to try to keep it short, but this is, again, there's a lot of ideas coming together here to really illustrate this stuff. So I hope this video helps with that. And we'll be back with another one.